Hello everyone and welcome. I'm back with the old pencil and paper today simply because I anticipate this one's going to be a little bit longer than the others and I'm not sure if my computer can handle running a screen recording software for that long. So we're going to go back to the basics here. What we are talking about today are theorems involving angles inside of a circle. There's a lot of them for us to remember, so it's important that we just go through them one by one, and yeah. So, I'd recommend getting a sheet of paper or a note app in your phone or something to jot these things down as I go along through them, because one, remember, the actual process of writing engages a different part of your brain, and it actually helps you remember things more efficiently, and it also gives you a one-stop shop to get all this information later. So, with that being said, there are a few definitions we need to cover first. So, to start, I'm going to draw my circle. Wonderful. So, here's my circle, and as always, I'm going to call this circle O. Now I say, as always, it's not always called O, but the circle is always named after the center. So, we're going to start with the simplest kind of angle, which is what's known as a central angle. A central angle is very simply an angle whose vertex is at the center. An angle whose vertex is at the center. Now, hopefully you can already picture what that means. Here's my circle. There's the angle. So, I have some unknown angle in here with an unknown measure. Now, I'm going to go through and I'm going to call this A. I'm going to call this B. So let's say, in the case here, what I want to know is the measure of angle AOB. And I'm going to go through and I'm going to say that this arc, the measure of arc AB, the minor arc, is going to be 115 degrees. If this is all you were told, you can tell just by looking at this diagram whether they're talking about minor arc AB or major arc AB. It's less than 180 degrees, so it's got to be the minor arc. And again, sometimes I'll do this thing where I'll just kind of trace out the outside of it like that, just so I know what arc I'm talking about. Or if you're working on, homework or your own problem where you've got access to them, you can use a colored pencil for something like this as well. Just to go, okay, 115 is my blue arc there. So, what's the relationship between a central arc and central angle and this arc? Well, in order to show you that, I want to show a little example that can hopefully motivate the reason for you. I'm going to draw a small circle up here as my example. Now, if you ever remember me talking about certain angles like this one here. The angle I'm drawing up here is exactly 1/4 of the circle. Since a circle is 360 degrees, I know this angle here is a 90-degree angle. The arc that this angle traces out, and by the way, the word for that, we would say that this angle subtends that arc. That's a word you're going to be hearing a lot of, so you want to make sure you know what it means. Subtends, S-U-B-T-E-N-D-S, subtends. An angle subtends an arc, meaning this angle is subtending arc AB. In this case, this 90-degree angle is subtending 1/4 of the circle. It's the part of the circle that it traces out. Since this is 1/4 of the full circle, it would be 90 degrees. Immediately, you see a relationship here. Central angles are equal in measure to the arc that they subtend, and that's the first rule you want to know, the first little theorem we have here. Central angle is an angle whose vertex is at the center, and it is equal in measure to the arc it subtends. So in the example problem I was given here, the measure of arc AB is 115 degrees. So this central angle, AOB, must also be 115 degrees. Now, how do I know that that's a central angle? Nothing told me it's a central angle. Well, if the problem said circle O, and they called this AOB, I know it's a central angle because its vertex is there. So realize they're not always going to tell you it's a central angle, but you can infer it from what's been given. I'd like to do one more quick example of these. Let's see how well, yeah, we can use the back, sure. So, again, I am going to draw myself a nice friendly little circle here. And I am going to plot my center. Oop, I'm a little off. Yeah, like that. And we're going to say that this is circle C. And I'm going to go ahead and say that this is G, F, P, Q. Now, you might be given a problem with just this diagram and a sentence explaining what you have. In circle C, diameters FG and PQ are drawn. With the measure of arc GP equals 140 degrees. Find the measure of angle QCG. Go ahead and pause the video and try to figure that out on your own real quick. So, I know it's circle C, which means C is the center. What I'm being asked to find is QCG, which means I want to find the measure of this central angle. There's two ways I can do that. The first way is if I find the measure of this arc, I know this angle is equal to that. Or if I find the measure of this angle next to it, I can just subtract from 180 to find that one. I think that's going to be the easier way to do this one, since what they've told me is arc G to P is 140 degrees. That would make GCP, this angle, equal to 140 degrees. So then I can just subtract off from 180 to find that my answer is 40 degrees. The other way you could do it, which is a little less straightforward, but you know this is a diameter. I don't know if you can hear that car horn honking in the background, but it's very distracting. I know that this here is a diameter, which means that this part of the circle has to be 180 degrees. So if that's 140, that arc is 40, and so the angle that subtends it is 40 degrees in measure, just like that. So those are our deals with central angles. Central angles are super, super easy, especially when you don't try to remember that little property. Instead, you just remember the idea that we define the measure of an arc to be based around a central angle that would subtend it. That makes that relationship, that they're equal, way easier to keep in mind. Next kind of angle we're going to talk about is equally as simple. It's not much more radical, but it's just another one to keep in mind. Sometimes people mix these two up, but they're real simple rules. Here's my circle. Now, I am going to first plot my center. I'm going to call this one circle E. Now, in this case, we're dealing with what's known as an inscribed angle. Remember, we've talked about that word inscribed before. We've talked about how every triangle can be inscribed in a circle. Meaning if I have a triangle like this, I can always draw a circle somewhere such that each one of those points lies on that circle. And that's a bad freehand. Maybe that one's a little bit better. Inscribed, meaning each vertex is on the circle. Inscribed literally means written within. So an inscribed angle is very simply an angle whose vertex is on the circle. So what does that look like? I take my circle. I'm going to place its vertex right now. And I'm going to go ahead and just label a few things here. That'll be B, that'll be A, that'll be N. And so, let's say in this problem, I'm told that arc BN is equal to, well, in fact, I can go ahead and I can find out exactly what it's equal to. Ooh, if I had a protractor, which apparently I don't. Thought I did. So, here to here, we're going to say that that is 120 degrees. Doesn't really matter, it's just an example, but still. Let's say that's a 120 degree arc. I want to know the measure of angle BAN here. First thing to point out, I'm going to draw another circle down here just to highlight this idea. Oops. Oh well. I'll need the whole thing anyway. Let's say in this problem down here, I'm going to go and I'm going to draw another 90 degree central angle. Roughly. But I'm also going to draw an inscribed angle that subtends the same arc. You with me here? This angle here traces out this portion of the circle, which is the same as this one in here. Now in this case, since this is a 90 degree angle, I know that this arc up here also has a 90 degree measure to it. But this angle here is definitely not 90 degrees. What's the relationship there? It winds up being that any inscribed angle has a measure that's half of the subtended arc. So an inscribed angle is an angle whose vertex is on the circle, and its measure is half of the arc it subtends. Meaning in this case, this angle down here must be 45 degrees. So in the main example I gave you, if arc BN had a measure of 120 degrees, down here, angle BAN must have a measure of 60 degrees. Now, that is the rule you need to know. The result of this rule is actually a super freaking cool proof. Y'all have been asking me why, or give an example, or give a reason, give the proof for a rule we have used since the beginning of the year. The angle sum theorem, or the sum of angles in any triangle, must always be That's right, 180 degrees. Why? Well, in this circle, I'm going to draw a random triangle that is inscribed. And we're going to just label these points A, B, and C. Angle A up here, well, that's an inscribed angle. And A subtends this arc. I don't know what the measure of angle A is, but I know that arc BC has to equal double whatever that is. Easy enough. Now I have angle B here. B subtends this very large arc. Again, do I know the measure of this big arc? No. Do I know the measure of angle B? No. But I know that B is an inscribed angle, and since it's inscribed, arc A to C, well, that measure just has to be double whatever B is. So this blue arc here is twice whatever the angle of B is. And lastly, C. This guy subtends this arc up here. It's double whatever C is. If you notice, all of these arcs, there's no gaps, there's no overlaps. These three arcs together have to add up to the full circle. So I could say that 2A plus 2B plus 2C has to equal the full 360 degrees. And if that's the case, I can just pull a 2 out. Which means that A plus B plus C must be 180 degrees. Very simple and elegant proof, but we had to wait until we got to circles to do it. Any triangle can be inscribed in a circle. Using that, what's called a lemma in a proof. A lemma basically means a stepping stone. So in a proof, a lemma would be something you've proven in the past that you're going to use. It's fundamental to get to where you want. Using that fact as a lemma, I could take any general triangle and say, since each of its angles are inscribed in that circle, they each subtend a unique, non-overlapping, distinct, or what's called a discrete arc. I know that the sum of those arcs has to be 360, and since they're inscribed, the angle sum has to be 180. It's a fun, beautiful way, and I just love that proof so much. So, those are central... Wow, what is this paper made of? There we go. Those are central angles and inscribed angles. Now we're going to deal with a set of angles that are a step more difficult. Interior angles, or angles inside of a circle, depending on who you ask. Again, remember, whenever you use a compass, you'll find angling the compass like this makes your lines a little bit more smooth. Here's a circle. Let's call it circle P. In circle P, chords AN and ET are drawn as shown. Well, if I'm saying they're drawn as shown, I better show them, huh? A, N, E, T. Immediately. Are these chords intersecting at the center? No. Are they intersecting on the circle? No. They're not central angles. They're not inscribed angles. They're something different. I can have angles whose vertex is here, or here, or here, right at the edge, or right near here. But if they're not on the center and they're not on the circle, they are interior angles, or angles inside the circle, and they have their own separate rule. Just to give you a sense of why these are a little bit more complicated. Let's say what we were told here is, well, let's dial it back a bit. Let's consider this angle right here. Say this is the one that I'm concerned with. It's my important one. Well, since these are chords, they're lines, which means that angle's the same. I know these two angles are equal, right? Are these arcs equal in measure? No. So there's no straightforward rule as far as, oh, it's just equal to this arc, or it's just equal to half of that arc. It's different arcs making up the same angles. So the property, the rule here, involves both arcs. So I'm going to give it to you. I'm just going to tell you it straight off. Any interior angle in a circle theta has a measure as follows. First of all, you know it has to do with both of these guys. They both have to show up there somewhere. And in this case, this one right here, if I take Tn and AE and I add them up and take half of that, I'll get theta. In other words, any interior angle has a measure as follows. Theta is equal to half the sum of the arcs it subtends. Meaning, theta is equal to 1/2 of the measure of arc Tn plus the measure of arc AE. So, if I was told that this arc here was 30 degrees, and I was told that theta had a measure of 70 degrees, and I said, find me arc AE. Well, I can just plug in here and say, well then 70 is equal to 1/2 of 30 plus arc AE, or I could call that X. And I don't want to take half of my unknown. Instead, I'm just going to multiply both sides by 2. 140 equals 30 plus AE, which give me that AE is equal to 110 degrees. Now, I just want to point out something here. It is purely coincidental that if this is 70, this angle here is 110. Purely by coincidence of the numbers of this problem. It has nothing to do with any rule there. So don't think it's just, oh, it's just the supplement of it. No, that just happens because I have weird numbers here. There is another way to do this one, which is, I wouldn't really recommend it, so I'm not even going to tell you how to do it. I'm just telling you. It's a simple enough rule that we're going to do another example here. In this one, I'm going to set up the problem. I'm going to ask that you just pause it once you have it set up and try to figure it out on your own. So, I'm going to take my circle. Boop. And here's what we're going to do. We are going to say that since there's the center, Go ahead and find x. So, hopefully, the way you had done this is recognized that since this is the center of the circle, and my chords are not intersecting there, I have to use intersecting chords, interior angle, whatever you want to call it. I need to use the rule that tells me that this angle here, which is theta, this angle subtends these two arcs. So theta's measure is 1/2 of the sum of 80 and 110. I can't put my x there because this angle does not subtend those two arcs. I can find out what the measure of theta is by saying it's 1/2 of 190 to get that theta is 95 degrees. So then x is just going to be equal to 180 minus 95 to give me an answer of 85 degrees for my x. This is one that had another way of doing it. First of all, this here is an 80-degree angle. Do I know what this remaining part is? Be very careful. Some people might be tempted to say, oh yeah, that's 90 degrees, or excuse me, that's 100 degrees, because they have to add up to 180. This isn't half of my circle, it's not a diameter. But what I can say is that since these two add up to 190 degrees, these two have to add up to 170. So if any interior or angle inside of a circle is half of the sum of the arcs it subtends, I could say x is 1/2 of 170 to get my 85-degree measure. That's a really unnecessarily tricky and roundabout way of doing it. I wouldn't do that unless for some reason you absolutely had to, which you don't. In this problem, I would rather just find this guy and then subtract to get it. In reality, you're kind of doing the same math, you're just doing it in different places. Just be careful. Realize that there is more than one way to skin a cat, but sometimes it's not worth skinning it at all. Okay, so those are our inscribed angles, our central angles, and our angles inside the circle. Now we start dealing with the ones that are more complicated. The reason these are more complicated is because the equation I'm going to give you is very similar to the last one. So, here's my circle. We're going to do a quick little recap here. This thing here is a central angle. It is equal in measure